continue our discussion of hybridization expansion impurity solvers. I will adapt the program a little bit because there was a request that I should discuss the strengths and weaknesses of the different approaches. So let me start by discussing how we can generalize this segment formalism, which I explained for the Anderson impurity model, to completely general multi-orbital systems. So and this generalization is not doesn't work with these segments anymore, but it involves matrices, so that's why I call it a matrix formalism. But the first point I want to make is that it's very clear that this segment method, which I explained in the last lecture, can be immediately generalized to multi-orbital systems which have only a density-density type interaction. So suppose we have an interaction of the type U alpha beta, N alpha, N beta, and we have several orbitals. So these are now orbital and spin indices here. Then we can just for each flavor, say spin and orbital, let's call this a flavor, draw one of these timelines. So alpha, beta, gamma, and we can place our operators on top of these segments, like this. And then we just compute the overlaps of these various segments and the lengths of these segments. So we have, for example, here we have an interaction U alpha beta. Here we will have an interaction U beta gamma, which can be different. And here, say we have an interaction U alpha gamma, and so forth. And so we can immediately apply this technique to this kind of multi-orbital systems with density-density interaction. But now we in order to treat more general multi-orbital systems where the local Hamiltonian is no longer diagonal in an occupation number basis, this separation and segment representation doesn't work anymore. But we may simply view our configuration more generally as a single timeline with operators of different kinds. So for example, this configuration we could draw as follows. We have, for example, a triangle operator like this, corresponding to the gamma. And the beta, say, is a square. And the alpha remains a circle. So we can draw our configuration simply like this, where this corresponds to alpha, this corresponds to beta, and this corresponds to gamma. And now there's no specific restriction on the sequence of operators. For example, we can have two creation operators in sequence, or we may have two annihilation operators. So, yeah, we simply we can view our configuration simply as a collection of operators with different flavors. And then these collections of operators have the weight, which I have already written on the board, namely trace d e to the minus beta h local, and then some time ordering, some product over all flavors. I call them alpha now. And then we have d alpha tau alpha n alpha. And so for each flavor we have a product of creation and annihilation operators. And then we have, in the case at least where the hybridization is diagonal in orbitals, we have a product of determinants like this, and then d tau to the 2. So this is quite generally the expression, and this in principle works for an arbitrary interaction. So in principle, this works for an arbitrary u alpha beta gamma delta d dagger alpha d beta d gamma d delta. We just have to somehow evaluate this trace factor. And so how do we do this? I mean, this trace factor can now be viewed as a trace of a matrix product in some suitable basis. We express all these operators here as matrices in some convenient basis, and then this trace simply becomes the trace of the matrix, corresponding matrix product, which we have to evaluate. So the trace here is something of the form. We have some time evolution operator. Then we have some creation or annihilation operator of some kind at time tau m, and then we have another time evolution operator. And so forth, and then we have a first creation or annihilation operator and a first time evolution operator. So what I've done here is I've simply written out the time dependence of these operators, which is given by this local Hamiltonian, and now all these d alpha and d dagger alpha are some creation or annihilation operator, which I call O. So we have a sequence of time evolution operators sandwiched in between these creation and annihilation operators. And now we have to evaluate, we have to express these operators in a convenient basis and evaluate this product. So what we have to do is express all these operators in a suitable basis. Where n is the dimension of the Hilbert space, of the local Hilbert space. And compute then the trace explicitly. And so here you see the problem of this general approach. This dimension of this local Hilbert space grows exponentially with the number of orbitals in your impurity problem. So these matrices that I'm talking about here become quite large. For example, for a 3-orbital model, this will be 64 times 64 matrices. For 5-orbital models, these are 1024 by 1024 matrices. And so the computational effort grows very fast. And in practice, one is limited to basically 5 orbitals. Yeah, so this is the problem. So we have to find now a reasonable strategy to deal with this. And so the first strategy, which I call strategy 1, is to go to the eigenbasis of the local Hamiltonian. In this eigenbasis, at least these time evolution operators will be diagonal and very easy to treat. So e to the minus tau h log becomes a diagonal matrix. Where the A1, E2 are the eigenvalues of h local. So in this basis, these time evolution operators are very simple, but these creation and annihilation operators are not simple in this eigenbasis of the local Hamiltonian. But at least if we order these eigenstates according to certain conserved quantum numbers of the local Hamiltonian, we can make sure that these operators have some relatively sparse block structure. So let me, here. So this, in this eigenbasis, the OM, these matrices OM are in general complicated. But with a block structure. if we group the eigenstates according to conserved quantum numbers. What are these conserved quantum numbers? Typically, this is the total number of electrons on the impurity. The local Hamiltonian will not change the total number of electrons. It can, in some cases, be momentum. So if you have a 4-site cluster, you will have momentum as a conserved quantity, because this is like a ring, and things like this. So, and then these operators have a structure which looks more or less like this. So you have some, I don't know, some blocks like this, which are something like this. So most of it is 0, but you have dense blocks which connect the different sectors, quantum number sectors, for example, particle number sectors, like this. And this one has to compute then and evaluate the matrix, the block matrix products explicitly. So then the trace calculation becomes a sum over all the contributing blocks which I call M. And we only have to trace over the states in this subspace M. And then it is just some kind of block matrix product or minus well, these are diagonal and these are relatively small blocks. So with this, the procedure is numerically manageable up to certainly 5 orbitals. 7 is yeah, I think 7 is not really doable, with modest effort at least. There is this alternative approach, which at first looks a little bit strange perhaps, but turns out to be more efficient, at least for large multi-orbital systems, and that's the so-called Krylov approach. And the idea here is to stay in the occupation number basis. So here, for this approach, we have switched to the eigenbasis of the local Hamiltonian. For the second approach, we stay in the occupation number basis. And we use the fact that in the occupation number basis, both the local Hamiltonian and these operators, creation and annihilation operators, are very sparse. So in this basis, both H local and these creation and annihilation operators, which I call OM, these are very sparse. So we can, for example, in this basis very easily apply a creation or annihilation operator to some vector. And the only challenge then is to evaluate the time evolution operator in these spaces. But still we can relatively efficiently evaluate the time evolution operator applied to some given vector. That's what we do. So we want to evaluate something like e to the tau h local applied to some vector in the occupation number basis. And this we can do efficiently by defining the so-called Krylov subspace. So we construct the Krylov subspace and this is the space spanned by the vectors v, h local times v, h local squared times v, and so forth, up to some power p. We construct this subspace, and within this subspace we can very well approximate the time-evolved vector. And it turns out, for most practical purposes, we need a very small subspace of maybe 2 vectors to get a good approximation of the time-evolved vector. So these Krylov spaces, which we need to go from one operator to the next, is usually very small. And then we transform to these spaces. We evaluate the time evolution, and we transform back to the occupation number basis. And that's how we can propagate one vector through this whole trace. And we do this for at least low energy states in the trace. And it turns out this approach, at least for large multi-orbital systems, scales much better with the dimension of the Hilbert space than these matrix products. Okay, so then the trace becomes just the sum over the, say, low energy states . Right, and so we, as I explained, with this Krylov approach, we can easily propagate now this vector. This gives a state psi prime in the occupation number basis. We can then very easily apply a creation or annihilation operator to this state psi prime, and then we proceed like this. And so the scaling is as follows. At least if we truncate the trace, the outer trace, to low energy states, then it scales as order dimension of h local compared to a cubic scaling for the matrix method. So with this approach, at least one can do 5 orbitals with reasonable effort, and maybe 7 if one is really ambitious. One can try 7, but not more than that. Yes? Why? Why only? Yeah, basically, well, I mean, for this you diagonalize the local Hamiltonian and you search for the low energy eigenstates, and then you can introduce a cutoff and you can check how many states do you need actually in this trace to converge the result. And at least at low temperature, it turns out you don't need many states. At high temperature, you need basically all the states, but at low temperature, it's enough to keep the few, basically the ground state, or if it's degenerate, the few lowest energy states. Okay, so that's it. So that's the generalization to arbitrary multi-orbital systems. Now what I want to do is explain how, at least sketch, how in this method we can measure the Green's function. And then from there I want to explain what is the meaning of the perturbation order in this formalism. So let me discuss the measurement of the Green's function. Yes.
Here, P should depend upon how large tau is.
Yes, yes. So this you have to do adaptively. So you build your Krylov space and you enlarge your Krylov space until this vector converges. Yeah. So it depends on the length of the time interval.
We can split tau into pieces, delta tau, and very such pieces, and very small.
Well, I mean, the length of tau is determined by the operator positions.
No, but single body can split it into smaller pieces and use a smaller gain.
Yeah, but I think you don't gain anything by doing that. Yeah, it's better to just adaptively increase the size of this Krylov space until you have a converged result. Okay, so let us look at the diagram for the Green's function. So let us look at the Green's function g of tau 0, which is something like t d of tau d dagger, something like this. So we want to measure this. Oh, okay, no, that's fine. Thank you. Or maybe this one is good. So how do the diagrams look for the Green's function? We have now two additional operators. We have an additional creation operator at time 0 and an annihilation operator at time t. And for the time evolution, we do this expansion in the hybridization. So we get diagrams which look something like this. We have time 0, time beta. Then we have some creation operator at time 0 and an annihilation operator at time tau. And in between we do an expansion. For example, we add an annihilation operator here and a creation operator here and another creation operator and an annihilation operator here. And then we can introduce again our segments. So I'm now for the purpose of this discussion I'm going back to segments, but it actually doesn't matter. Just to illustrate a little bit how it works. So we can have segment configurations like this. And these operators, which I have produced now by my hybridization expansion, they are somehow connected to the bath through hybridization functions. But these two operators are not connected to the bath because these are the operators I put in for the measurement of the Green's function. So these are connected via hybridization functions. And so this is a diagram which appears in the expansion of the Green's function, if we do this strong coupling expansion. And it has a weight which I call WC, and with an additional d at tau and d dagger at 0. This is a diagram appearing in the expansion of G. Now let us look at the other diagram, very similar one, which looks like this. So I have an operator here, I have an operator here, I have an operator here, sorry, yes, and here. And I connect all of them to hybridization functions. So this is the same configuration, except that I now have connected all the operators to hybridization functions. So this is a configuration which appears in the expansion of the partition function. And it has a weight which I call WC 0 tau. So this is a specific configuration which has operators at time 0 and time tau. Like this. This is a diagram with a creation operator at 0 and an annihilation operator at tau, which appears in the expansion of C. Of the partition function. Okay, and what you can see is that the trace factor for these two configurations is the same. So we have the same segment configuration for both. So there is some close relationship between the two, and that's what we are now going to exploit. Namely, we write our Green's function, g of tau 0, which by definition is 1 over c times the sum over all configurations times these weights, c, d dagger, d of tau, d dagger of 0. We write it by dividing this thing, dividing and multiplying by this weight here. So this is 1 over c, sum over c, wc 0 tau, wc d like this. And now we exploit the fact that the trace factors are the same, but the determinants are not the same. So here we have one less creation and an annihilation operator than we have here. So what this is, it's a ratio of two determinants, which I call n minus 1. And that n 0 tau minus 1, where n0 tau is the enlarged matrix, which has these additional hybridization lines attaching to the operators at 0 and tau. Okay, and so what is the difference actually? The difference is that this is the same matrix as here, as this one, except that we have crossed out one line and one column of this matrix. So we can write it basically like this. It's determinant of this matrix here times determinant of the same matrix, except that I eliminate this column J corresponding to D dagger, and row I corresponding to the operator D. And there is actually, we have to be careful about the signs. There is a minus 1 to the I plus J. And so this object here is called a minor, matrix minor. If we take the determinant of a matrix where we cross out one row and one column, and now maybe you have you all remember your linear algebra, so you can tell me what is this, the minor divided by the determinant. Was any? Exactly, yes. This is an element of the inverse matrix. Very good. So this is something like M, no, not M inverse, but M 0 tau Ji. So that's the inverse hybridization matrix element Ji. Okay, so basically what we find from here is that, so this is now the weight for the partition function expansion with some constraint on the operator position, but we see already that what we have to do is we sample, as usual, our partition function, and what we accumulate as a measurement are the elements of the inverse hybridization matrix. That's what we have to do. And now I'm going to, for the sake of saving a little bit of time, I'm going to skip a slight technical complication, which has to do with the fact that in this weight here we have constrained the operator positions. Basically what happens if we release the operator positions is we get instead of getting a specific element Ji corresponding to time 0 and tau, we can express it as a sum over all elements J and I of this matrix. But I think that's it's maybe a, or do you want to hear these details? I don't know. I'm afraid it's, I think we can skip this. This is a bit of a technical detail. So in the end, after some technical details, which you can look up somewhere in one of the papers, we get the following expression for the Green's function. It's basically the Monte Carlo average of the sum over all elements of this inverse hybridization matrix with a factor 1 over beta times a delta function. Minus tau prime J. So the Monte Carlo average, well, this is a sort of beta antiperiodic delta function, which is defined as follows: delta tau prime is delta of tau minus tau prime if tau prime is bigger than 0, or minus delta of tau minus tau prime minus beta if tau prime is less than 0. So it's a sort of a beta antiperiodic version of a delta function. So what we do here is we sum over all operator pairs, creation and annihilation operator pairs. We measure the distance between them, and then we accumulate a delta function with the weight given by the Ji element of this inverse hybridization matrix. So Mij, this is inverse So in the code, if you implement this code, you always work with this inverse matrix, and that's why in the weight I put this m-1, because actually the object you will always handle in the computation is the inverse of this hybridization matrix. Anyhow, that's the formula for the Green's function. And
accumulating the data by g tau using this formula, you will take the data and break it up into small chunks.
Yes.
Times tau minus tau prime satisfied from just add it.
Yes, exactly. In practice, you use a very fine grid, and whenever within the accuracy of your grid, this tau I minus tau prime falls into this grid point, you accumulate this value. That's how it works. In principle, one can also directly Fourier transform and measure the Matsubara components of the Green's function simply by Fourier transforming this formula, and then you find that the formula for the Fourier components is like this. Like this, one can also directly accumulate the Matsubara coefficients. Okay, and now we are going to use this formula to evaluate a quantity which will turn out to be interesting, and that's the convolution of the Green's function and the hybridization function. So let us now, just for fun, compute the following convolution: Green's function of tau, hybridization function of beta minus tau. So what is this? We just plug in now our expression for the Green's function. That's this, and now because we have a delta function, we can easily do this time integral. And if we use that this hybridization function is a beta antiperiodic function, we will find that this is minus 1 over beta sum ij prime ji delta of tau prime j minus tau I. Okay. Yes.
In this ratio of determinants, is there a delta tau square also involved?
No, because these two special operators here have put in by hand, so there's no d tau associated with these two guys. So here we don't have d tau squared. But right, we are now just going to use this formula again, so it's good it's here. So for mji, basically we are going to use this expression. So this is something like minus 1 to the I plus j, then a ratio of two determinants, namely the determinant of the full matrix times the determinant where we have crossed out row I and column j. And this matrix here is basically the delta, the inverse, this is the hybridization matrix, not the inverse hybridization matrix. And so in particular, the element here, which we have crossed out at the intersection, what is this element? This element is delta, by definition of this hybridization matrix, is delta of tau prime j minus tau I. So now what do we see here? Let's just fix I and look at the sum over j. So we have sum over j minus 1 to the j times the minor ji times delta minor of the hybridization function times delta tau prime j minus tau I. Now again, one of the students can tell me what this is. This is just the expansion of the determinant along the row I. Yes, this is the expansion of the determinant along the row I. So this is itself, again, just this determinant of the hybridization matrix. So what we have here is nothing else than minus 1 over beta expectation value sum over I, and then we have the ratio of the two same things, like this. And how many I do we have? We have as many as we have perturbation orders in our configuration. So this is minus 1 over beta times expectation value of, well, n is not the density here, but the perturbation order. Maybe I should call it k. So that's the perturbation order. So that tells us what is the meaning of the perturbation order in the hybridization expansion. It's essentially beta times the convolution of the Green's function times the hybridization function. And now we have to discuss what is the physical meaning of this convolution of the Green's function and the hybridization function. And within the dynamical mean field context, the meaning of this convolution is the kinetic energy. And I'm trying to sketch this, how I hope I can remember it correctly. So what is the kinetic energy? Let's consider it for one spin component. Kinetic energy for one spin component is sum over k epsilon of k n of k. So n of k is the occupation of the momentum state k, right? And so this n of k we can write as g sigma of 0 minus, I think, if we use the convention where the of like this. So we basically get sum over k, sum over n, e to the I omega n 0 plus epsilon k g k sigma I omega n. And what is g k sigma I omega n? That is 1 over I omega n plus mu minus epsilon k minus self-energy sigma. And now we do some trick. So now we have to do something with the this epsilon k here. And what we do is we write it first in the same form as the denominator, which has an epsilon k, and then correct for it. So this gives, so let's forget about this 0 plus here, then we have sum over k, sum over n, then we have minus so this gives us the epsilon k. Okay, so I think so far we are still okay. So you just correct me if I made a mistake. So basically I've just written this epsilon of k here as the sum of these two terms. And I think that looks okay. And now what we use is that this gives us minus 1. And here we have something which only depends on epsilon of k in the denominator. So basically what we find is the following. Sum over k, sum over n, minus 1, plus I omega n plus mu minus sigma divided by I n plus mu minus epsilon k minus sigma. Now at this point we can switch to density of states integral and compute or simply evaluate the sum over k. And what this gives us is the local Green's function. So we get here, together with this k sum, we get G local times I omega n plus mu minus sigma. And now we have another expression which links the local G, the sigma, and the hybridization function of the impurity system. So we have something which I think is only I something like this. And this we are going to plug in here. So this is something like G local minus 1 plus delta. And now this G local minus 1 times G local gives 1, and that will cancel nicely with this minus 1, so we get rid of this guy. And what remains in the end is sum over n G local, which is simply G. So that's our G delta I omega n, and that's precisely the Fourier transform of this convolution here. So that shows that the kinetic energy per spin is exactly minus beta times the average perturbation order. So that's what we learned here. So the average perturbation order for the corresponding spin component, and so the total kinetic energy is just the sum over the two spin components minus beta sum over sigma average k sort of sigma. So now we know that in the hybridization expansion, the perturbation order goes like the kinetic energy. So now the question is, how is it in the weak coupling expansion, which Michel Ferrero discussed about 2 days ago? How does the perturbation order scale? Did he discuss this point? Maybe not. Then let's briefly derive it. That's actually quite simple. So let's now switch to the weak coupling expansion for a minute. So this was hybridization expansion. So let's switch to the weak coupling formalism and let us look at the expectation value of H local. So the weak coupling formalism is based on a stochastic expansion in the interaction part, or maybe more generally in the local let's just take the interaction part. So the local part has in principle the chemical potential contribution also. So H interaction we can write as 1 over beta integral from 0 to beta tau, something like this. And now, to evaluate this expectation value, we do this weak coupling expansion as Michel Ferrero explained. And what this will give is something like 1 over beta and now an additional sequence of time integrals d tau 1 to d tau k, 1 over k factorial, and then we have trace over e to the minus h0 beta, where h0 is now the non-interacting part of the problem, and then time order, and then we have something like minus let's for the sake of this for the sake of this argument, consider a minus h interaction. Then we have minus h int of tau. That's the operator we get from this integral, and now we get additional operators from the expansion of the time evolution in this expectation value. So we have minus h int tau k minus h int tau 1, like this. And so what we now do is we have these k integrals from the expansion, and we have another sort of additional integral which comes from this trick here. So what we now want to do is just treat this like an ordinary time point in our expansion. And to do that, we just write this guy here, this k factorial, as k plus 1 divided by k plus 1 factorial, and just call this guy tau k plus 1. And then we are back to basically exactly the same expression as we would have in the normal partition function expansion, except for this additional factor k plus 1 here. So we can write this expectation value of the interaction Hamiltonian So we can write minus h int as sum over some configuration, which is now the configuration which has k plus 1 time points. Then we have the number of operators in this configuration of k plus 1 time points, so that's k plus 1 here times the usual weight of this configuration C. And so that's nothing else. And we have a factor 1 over beta here. So that's nothing else than 1 over beta, the expectation value of the perturbation order in the weak coupling expansion. And so there's something a little fishy with this minus sign here, but we have to think a little bit what one actually wants to expand in, whether it's the local part, which has the chemical potential, or just the interaction part. But basically, what one finds from this type of argument, this is basically U times the double occupancy, like this. So we find that the average perturbation order in the weak coupling expansion grows like beta U times the double occupancy, or basically K in the interaction expansion goes something like beta times E potential. So that's for the weak coupling approach. And so this analysis tells you in which regimes these two methods are efficient. Namely, obviously, the weak coupling approach is efficient in the regime where the kinetic energy is large and the potential energy is small, whereas the hybridization expansion approach is efficient in the regime where the kinetic energy is small, but we don't care about the interaction energy. For example, in a Mott insulator, the kinetic energy is very, very small. This is a very efficient approach, whereas this is good in the weak coupling regime. And so what we have done is if you do DMFT with a semicircular density of states, of say bandwidth T also, then we have the interaction U, the perturbation order K. Mott transition is somewhere around 5 to 6, depending on the temperature. And then what one finds if one computes this average perturbation order for some reasonably low temperature, basically it goes up almost linearly in the weak coupling approach. Whereas for the hybridization expansion, it does something like this. So something like this. And the crossover here is around 1. So for zero interaction, the weak coupling approach is immediately exact. It doesn't have to do anything. Whereas the hybridization expansion approach has to work relatively hard to get the non-interacting problem right. But then pretty soon, for U around 1, the perturbation order becomes smaller in the hybridization expansion approach. And near the Mott transition, it's actually a big difference already. So order of, I think it was about a factor of 40 or so at the Mott transition. And of course, in the Mott insulator, it's very easy for the hybridization expansion, very hard for the weak coupling expansion. So at least for single site, single orbital Anderson problem, this hybridization expansion approach is far more efficient than weak coupling approach, and also for single orbital impurity models with only density-density interaction, this hybridization expansion approach is very efficient because it has this, doesn't have any exponential scaling in the density-density case. On the other hand, if you have complicated interactions, this approach scales exponentially. This approach scales in principle like a power law, but typically encounters bad sign problem if you have arbitrary Coulomb interactions. So in that regime, we still prefer the hybridization expansion solver, but it's not cheap anymore. So it's quite a big effort to do solve a 5-orbital impurity model with complicated interactions. Like spin flip terms, correlated hopping terms, things like this. Everything other than density-density. Well, the factor doesn't really scale, doesn't matter, because both of them scale proportional to beta. So that scaling is the same with temperature, but the scaling with interaction is different. But there's one case where the interaction expansion is better, and that is if you want to do say a cluster calculation for a simple model like the Hubbard model. You want to do DCA or cluster DMFT calculation for the Hubbard model. Then this weak coupling approach has this power law scaling. It scales like the third order in the size of the cluster, at least if there is no sign problem. Whereas this hybridization expansion approach for a cluster which has hoppings between the sites scales exponentially. And so you cannot go beyond 8 sites for sure. So that's why this weak coupling approach is used for large cluster calculations, and that's where it's efficient. And the strong coupling approach is used for single site multi-orbital problems typically. That is the most efficient one. Yes? Okay, I was just wondering what should I do in the last 15 minutes, because it's almost impossible to discuss these retarded interactions in 15 minutes. So we can discuss the sign problem. But basically the point is, it's probably easy to see that if you have this segment representation like this, so what we have discussed up to now are these instantaneous interactions like this. But in principle, you can, of course, treat retarded interactions. So you have an interaction between this and this point with some retardation. Or you have an interaction between this and this point with some retarded interaction. You can just evaluate it. And if you do the calculations, it's actually very simple. And what you end up with in the end is a formalism which looks exactly the same as for the static interactions, except you have some additional lines in your diagrams which connect all pairs of operators like this. And these lines are somehow defined by the frequency dependence of your interaction, but otherwise everything remains the same. This is the structure of your diagrams which you have to sample, and you know the explicit form of these lines here, and so in practice not much changes. But in these last few minutes I want to show now why does this hybridization expansion approach not have a sign problem. That's, I think, an interesting point and something, suitable thing to finish this discussion. And in order to show this, we use a special basis to to evaluate our the weights in the strong coupling expansion. So the first thing, I'm not sure, I haven't followed all the lectures because of somehow a busy schedule. But I assume you have seen or discussed that we can map the Anderson impurity model onto a one-dimensional chain. Has Thomas discussed this in the context of NRG or not? Okay, so let's just briefly go through this. So we have this impurity model with one interacting site and then many non-interacting sites connected to it with hybridizations V of P and energies epsilon of P. And we can represent this impurity model in a different form, namely as a semi-infinite chain where our interacting site marks the end of the chain, and then we have a one-dimensional chain like this. So we have U, mu, then we have minus V, minus T1, like this here. And this mapping from this topology to this topology corresponds to a transformation of the operators, of course, which I will write as follows. So we go from the D and C operators of this representation to operators D. So the first operator is not transformed, but the others are transformed into C1 prime, C2 prime, and so forth. And this D operator I can in general call then C0 prime. And this transformation is done such that the single particle Hamiltonian becomes tri-diagonal. So it's a tri-diagonalization of the problem. So we go from a Hamiltonian, which looks like this. We have minus mu here, and then the energies epsilon P1, epsilon P2, and so forth. And then all the hybridizations, Vp1, Vp2 here, and Vp1 star, and everything else is 0. We map to a tri-diagonal matrix, which looks like this, minus V. So this we can do with some transformation called householder transformation, or maybe the other names associated with this tri-diagonalization procedure. And one important point which we will need is that in this transformation we can choose the signs of these hoppings. So there's like a gauge degree of freedom in this transformation, so we can choose all these hoppings positive. Actually, explicitly, this V is just sort of the total hybridization of the impurity. So V, we don't really need it, but V is something like some P, Vp squared, and then the rest of the hoppings and these energies here, they come from the bath part. Okay, and now let us evaluate our weight of an arbitrary hybridization expansion configuration in this particular chain basis. So the trace, of course, is basis independent, so we can either evaluate it here or here. And so here it's just now a trace of the C prime states in the chain basis. So that's the last thing which we will do. Okay, what do we have to evaluate, really? That's the following trace. Let's go. Oh, sorry. So here I missed the H local plus bath part, sorry. Like this. So we have three types of matrices in our trace. So this is a product of three types of matrices. So the first is the matrix minus H hybridization D dagger, which in this chain basis becomes very simple. So the hybridization term was the term which described the hopping from the impurity into any of these bath states. But after the transformation, this has collapsed into just the hopping from this correlated site to the neighboring site. So this in the chain basis is now simply V times C prime 0 dagger C prime 1. And similarly, minus H hybridization D in this chain basis is nothing but V times C prime 1 C dagger C 0 C prime 0. And because we have chosen our V positive, or in fact, because they always appear in pairs, these matrices are positive. So there's only one element in this matrix which is non-zero, and that's V, and that's positive. So these two matrices have only positive elements, namely they have one element that is V and that is positive, okay? And now the slightly more complicated case is this time evolution operator. So we have this operator e to the minus tau h local plus h path. And so what do we do with this? So this we write as follows. And now we look at the diagonal and the off-diagonal elements of this matrix in this bracket here. And first of all, we notice that the diagonal elements are all dominated by this 1. So we have a tau over n, which becomes very, very small, and certainly becomes smaller than 1 at some point. So the diagonal elements of this matrix are, for sufficiently large n, dominated by 1 and are therefore positive. So they are all positive. And what about the off-diagonal elements? This H local is just this guy here. Acts only on the diagonal. So the off-diagonal part comes from the bath, and basically is the hopping now between these elements of this chain, or the sides of this chain. But this, by our gauge choice, we have chosen to be positive. So all these Ti are positive. So it means so let's write what this is. So the off-diagonal terms are minus tau over n times h path. And explicitly, this is the hopping between the sides of the chain, and that is minus Ti C prime I dagger C prime I plus 1, something of this sort. And because we have chosen this guy positive and there are two minus signs, we see that all these off-diagonal elements are also non-negative. So what we have just proven is that this trace here is the trace of a product of matrices which have all non-negative elements. And so the product of these matrices is then itself a matrix which has non-negative elements. And of course then the trace of a matrix with non-negative elements is positive. So we have just shown that this is a positive quantity. That's a very general proof, which shows that at least in a case where the hybridization is diagonal and where we can map the system to a one-dimensional chain or some sort of star-shaped structure, we don't have any sign problem in this hybridization expansion approach. Yes?
What happens in multi-orbital?
Yeah, in the multi-orbital case, it matters a bit what type of terms you have. If you have only, density-density type interactions so that you cannot exchange particles. Say you have two orbitals with spin. Your geometry is something like this. But in the impurity itself, you don't have hopping between the orbitals. You only have density-density interactions. So basically, you don't have a hopping here. You only have interactions. And so there's no particle exchange anywhere in this structure, so you don't have a sign problem. Basically, the same proof applies. On the other hand, if you have a cluster of sites where you really have hoppings between the sides of the cluster, you can have a particle exchange within the cluster, and then this proof doesn't apply anymore, and you can have a sign problem. But basically, the experience also with other calculations with complicated on-site interactions, including pair hopping and spin exchange terms, as long as the path is diagonal, there's essentially no sign problem. But if you have off-diagonal hybridization, it can be a very bad sign problem. And I think with this little insight, I think it's a good time to stop. And so thank you for your attention.
Thank you very much. That was really instructive. Questions?
What I observed is that with the hybridization and the self-energy and Green's function has a large noise at high frequency, but it's not there in the interaction expansion. Now people are coming with the Legendre polynomials. Why this method is generating large noise at the high frequency? It's violating the causality of the self-energy.
Yeah, that's the reason is that in the weak coupling expansion, you measure, if you look at the measurement formula in the weak coupling expansion, you measure the Green's function as a correction to the non-interacting Green's function. And this correction term, so this correction term goes like 1 over I omega n squared. So the leading term is sort of your initial bath, non-interacting bath Green's function, which gives you the dominant 1 over I omega n tail. And what you measure in the weak coupling expansions are only corrections to this 1 over omega tail. Whereas in the hybridization expansion, at least in the way I explained it today, there is no leading, you don't measure the Green's function as a correction to some existing Green's function, but you simply measure everything from scratch. But there is a trick, and I mean, this Legendre thing is one trick, and we have, together with Hartmut Hafermann, we have developed a scheme how you can directly measure the self-energy from higher order correlation functions. You have to accumulate certain higher order correlation functions to measure directly the self-energy. And if you do that, you have the benefit of also automatically sort of getting the right high frequency tail. So, and in practice, it's actually a non-issue. I mean, it looks ugly, but in practice, it's not an issue. And why is it not an issue? It's not an issue because your Green's function, say your local Green's function, is sum over k, 1 over I omega m plus mu minus epsilon k minus sigma. And so if you have a high frequency noise here, it is always dominated by the linear term here. So at high frequencies, this I omega n term dominates any noise you have in the self-energy at high frequencies. So in principle, this noise doesn't affect the Green's functions. It's just that you basically look at the wrong quantity.
Are there further questions? Okay. If not, there is a coffee break and you can still take Kathy.
Yes.
Inside class.
Okay, thank you.
Thanks.